In this question, we have a vehicle with two wheels, and the assumption here is that the wheels are rotating without slip. Therefore, there is a direct kinematic relationship between the vehicle speed and the angular velocity of the wheels. This goes for also the acceleration of the vehicle and the angular acceleration of the wheels. The relationship is through this radius, which is 0.6 meters. So I can write out a direct relationship as V is equal to omega r, and also A is equal to alpha r for this relationship because of this assumption of wheels rotating without slip. That being said, between these two wheels we have a link, and this link here is connected to the rear link by a revolute joint and to the other link by a revolute joint, and then also there's this horizontal freedom. That means at this point of connection no reaction force can be applied in the horizontal direction. The only type of force is in the vertical direction. However, at point P, we have a reaction force at the horizontal, vertical, and then horizontal as well. So we can name this as AY, and we can name this as BY, and also BX as the reaction forces. Now, the type of connection here happens to be at the same distance here, which is 0.4 meters from the center of these wheels. And as a result of that, it has the same link length, so it kind of looks like this 4-bar mechanism that we have discussed in our kinematics lecture, in the beginning of our kinematics lecture. If you remember that, you will also remember this coupler link's motion is a curvilinear motion. That means it does not rotate. The only type of motion it's going to have will be a translational motion, and it's a curvilinear translation. And as a result of that, the acceleration that's going to be measured on this link at any point will be the same. So if we can find out the acceleration at point B, it will be the acceleration at point G or at point A. So that's the information that we can derive directly. The mass of the link is given to us as 20 kilograms. The vehicle is moving at a constant 4 meters per second. That means the acceleration is equal to 0 and makes the angular acceleration to be equal to 0 as well. And from this quality, we can find the angular velocity, angular speed of the wheels as V is given to us. And we are asked to do the calculation when theta is 30 degrees. Now, in order to solve this problem, we're going to write out Newton's equation, F equals to ma. That's a vector equation. And as a result of that, we'll get two equations. And this A is the mass center's acceleration. We'll get two equations if we choose to use the xy coordinates in xy and y coordinates. And then we have three unknowns, AY, BY, and BX, which we want to find BY and BX. But at the end of the day, we have three unknowns. This gives us two equations. We need a third equation, and that will be the moment equation. We can use the moment equation about the mass center, and that will be the mass moment of inertia times alpha, but alpha is equal to 0. So this equation will be equal to 0, and the forces that are going to generate the moment about the mass center are AY and BY. There's another force acting on this link, which is due to the mass of this link and the gravity. So there's this gravitational force acting at the mass center, which is not going to generate any moment about the mass center. So the information that's going to appear here will be about AY and BY for this information. And then if you're going to write out an equation along the y-axis for the force, then that will contain again information about BY and AY. So two unknowns, two equations, I can solve AY and BY. And from the third equation, which is along the x-axis, I can solve BX. This is a way to find out a solution to find BX and BY. And then finally, find the magnitude of the force supported by the pin at B. So this is asking us about the magnitude of the reaction force at B. And we can find a solution in this way. Another way of solution is by making use of the alternative moment equation. In that case, we can choose this point A as our moment equations point. And in that way, what we do is we cancel out the effect of AY, because the moment that's going to be generated by AY at point A is equal to 0. And in this equation, the only unknown that's going to appear is by, because the moment by bx at point A is also equal to 0. Therefore, I can find out by directly from this alternative moment equation. So this is a direct solution, and we have this type of a solution in the lecture notes. In order to carry out the next calculations, we need some more information, and that information is about the acceleration of this point G. And we can find that acceleration by finding the acceleration of this link at any point, for example, point B. So we can write out an equation, and the acceleration of this point, we can name this point as O because it has the same acceleration of this O point, because the vehicle is moving together with these wheels, and the acceleration is basically equal to 0. So I can write out a relative acceleration equation between AB and AO, where AO is equal to 0, and this is the acceleration in the normal direction, and this is the acceleration in the tangential direction of this relative acceleration. This is A, B relative to O. Okay, this is our AB relative to O. These are vectors again. Well, alpha is equal to 0, so the tangential part of the acceleration cancels out. There is this normal part, and that is along the radius here towards the center of curvature. If point B will be located at the next sequence here, it will be still to the center of curvature. And at this instant, when theta is 30 degrees, if we show the free body diagram, this acceleration is with a 30 degrees from the vertical. Okay, so this is 30 degrees from the vertical. And we can do this calculation. The only term that's going to appear here for the acceleration is omega squared r. R is OB here, which is 0.4. And the resultant is also the acceleration of the mass. And this is its direction. Now we can write out an equation, the alternative moment equation for point A. In that case, on the left-hand side of the equation, we're going to have mg times the distance. The distance is 1 meters here, and the distance to B is 1.8 meters. And they are both shown here as downward direction. You can freely choose this direction, by the way, but this is already chosen for us in this notes as downward direction. So it is consistent with the direction of mg, so that's why they appear to be positive, all of them. If you choose by in the opposite direction, then you need to have a negative sign. Anyways, so this is the left-hand side of the equation. On the right-hand side of the equation, because alpha is 0, Ig times alpha should have appeared here, but since alpha is equal to 0, this part cancels out to be 0, and we have this extra information, which is ma times the perpendicular distance here, which is this d distance, which can be calculated by the trigonometry. This is 1 meters, and then this is 30 degrees, and we can find this d distance as 1 meters times cosine 30. There is that information. And in this equation, the only unknown is by, so there's that calculation. Then we write out an equation along the direction of x for the force, and we need to find the x component of this acceleration, which is going to be in the horizontal. So we use the sine 30 for that, mag sine 30. This is agx. And bx is the only force acting in the horizontal direction. Again, the direction of the arrow is consistent with our equation. This is in the positive direction if we consider the left to be positive, and ag's x direction or horizontal direction component is also to the left, so they appear all positive in this equation, positive and positive. And we find out the reaction force in the x direction, and then we can calculate the magnitude of this reaction force.